Hello everyone. After a brief introduction to the biocoordination chemistry, we will discuss about the oxygen binding proteins. So whatever biomolecules that are available, these biomolecules with the metals, we can broadly classify them into three different types. One being the oxygen binding proteins, the second being the electron carriers, and the third being the metalloenzymes. But for our syllabus, we only have oxygen binding proteins. So these are the proteins that bind the oxygen reversibly. Before getting into the details of these oxygen binding proteins, let's give some introduction about the oxygen and its interaction. Well, as a generalization, we are trying to compare the lifespan of a particular organism to the number of breaths that the organism takes per minute. We all know that oxygen is a source of survival for animal kingdom, including human beings. So we are trying to draw an analogy between the respiration and the lifespan. So just let me choose 4 examples. Apart from, I'm not including human being here. A giant tortoise which takes about 4 breaths per minute can live a very long life. It can live till 150 years. But if at all we see a mouse which breathes about 100 to 160 times a minute, it can only survive to a maximum lifespan of 3 years. So, well, the viewers have to decide whether there is a direct link between the number of breaths taken and the lifespan. Well, when it comes to the dioxygen binding proteins, these dioxygen binding proteins can bind dioxygen reversibly. So when I say reversibly, there is a equilibrium which could shift towards the right, or it could also shift towards the left. Whether the equilibrium shift towards right or left, that depends on the ambient temperatures and also the partial pressures of the oxygen. Whatever known oxygen carrying proteins that we have naturally, they contain either iron or copper at their active sites. For example, if you choose hemoglobin, it contains iron. Hemocyanin contain copper. Hemerythrin contain iron, and so on. Molecular oxygen, it exists in a triplet state, and also it is very reactive thermodynamically. So it is a triplet species. Now whenever it is combining with some living organisms, usually the reaction is not very fast. The reason for the reaction being not very fast is oxygen is in a triplet state, whereas most of the biomolecules, which are organic molecules, they are present in spin singlet states. So a spin triplet state is forbidden from reacting with a spin singlet state. For this reason, oxygen do not react very harshly with the biomolecules. The reaction is rather sluggish. So also we are trying to derive some relation between the stretching frequencies, the oxygen to oxygen bond length in a particular given species. Suppose if I choose some species, the first one being the dioxygen, which is a triplet state. The 2 unpaired electrons are present in the antibonding orbital. The stretching frequency is found to be around 1555 wave numbers, and the distance between the oxygen atoms being 1.21 angstroms. Now as more and more electrons are being added into the antibonding orbitals from 16 electron system, as it enters into the 17 and 18 electron system, antibonding electrons are being increased. As antibonding electron increases, antibonding character also increases, bond length increases, and as the bond length increases, the stretching frequency decreases. So as an electron is being added up to the dioxygen, the stretching frequency will fall. This is a clear indication that whenever dioxygen binds to metal, and if there is any fall in its stretching frequency, some electrons are being added into the dioxygen from the metal. And when we say that the stretching frequency fall, the dioxygen has to bind to the metal. So what are the various bonding modes where the dioxygen is binding to the metal? When it comes to the bonding modes of dioxygen, there are 3 important bonding modes. One is end-on, edge-on, second one, and the third one is side-on. End-on, again we have two different types, terminal and it could be bridging. In edge-on there is no further classification, whereas in side-on again there is a classification into terminal and bridging. So I can just draw the structure. Suppose if I say end-on, metal atom binds to the dioxygen. Only one metal atom is bound to one of these oxygens, whereas in bridging two metal atoms bind in an end-on fashion. So if I choose let me put a dioxygen here. Now for this dioxygen, these are considered as ends, these are considered as sides. This particular one is side, this is a side, this is an end, this is an end, and this is a edge. So if any metal atom binds here, we call it as a terminal. Any metal atom binds here, we call it as a terminal, end-on. And again, this is terminal, side-on. If one metal atom binds, we say side-on terminal. Two metal atom binds, we say side-on bridging. One metal atom binds, we say end-on terminal. Two metal atoms bind, we say end-on bridging. Suppose if a metal atom binds only in the center, only in the middle, then we say it is edge-on. If at all the metal atoms bind in this fashion, we say it is end-on. Side-on, so metal atom can bind here, or the metal atom can also bind here. Let us draw the structures. This is a side-on terminal. Side and side, this is side-on bridging. So these are the various bonding modes of dioxygen. Out of all the three bonding modes, the most commonly found bonding mode is the end-on bonding mode. Within end-on, terminal bonding mode is the most common one. So we conclude that the end-on terminal is the most common bonding mode of dioxygen. Again, in this end-on and side-on bonding modes, edge-on is very rare, so we are not going to discuss. In end-on and side-on, the bonding interactions where the orbitals overlapping could be different. I'll just show one of these orbital interactions. Suppose if I'm showing this metal, all this is in one phase, this one is in the another phase. Antibonding orbital of the dioxygen is being involved in this. These two are in the same phase, these are in the different phase. This is called as a sigma type of interaction. Now this is end-on, it is end-on terminal, only one metal atom is bound. Suppose if it is end-on bridging, another metal atom can also bind to this lobe of the oxygen atom. This is a sigma type of interaction. For this same end-on, we could also have a pi type of interaction when the orbital involved from the metal atom is different. Now here the oxygen molecule is not in the plane of the paper. You can just imagine that it is away from the plane of the paper, and this is a pi type of interaction where the metal atom is only bound to the one oxygen atom. This is still a terminal end-on mode, it is not a side-on mode. So within the end-on terminal mode, the metal atom can interact only with one lobe of the one of the oxygen atoms, or it could also interact with the two lobes of one of the oxygen atoms, which we simultaneously call as a sigma type or a pi type of interaction, which is end-on terminal. If another metal atom also binds to one of the lobes, or it may bind to two lobes, it is sigma and pi type of the end-on bridging mode. When it comes to the side-on, well, in side-on, the two lobes of the two oxygen atom interact with the two lobes of a metal. So this is a side-on and it is only to one side, so we call it as a side-on terminal. If at all there is another metal atom here and interacting with the two loops of two different oxygen atoms, we call it as a side-on bridging mode. So altogether we could have a sigma type or a pi type of interaction in the end-on terminal modes, where only one oxygen atom is involved. When it comes to the side-on, the two lobes of the two different oxygen atoms are involved. Then this is about the bonding modes of dioxysm. Now getting into the oxygen binding proteins, as we said, the three important oxygen binding proteins are hemoglobin and its unit myoglobin, hemerythrin and myohemerythrin, the third one being the hemocyanin. Before getting into the details of the hemoglobin, hemerythrin or hemocyanin, just let us have a small introduction about some macrocycles that are present in the biomolecules. A macrocycle is a ligand which is a cyclic ligand. In this cyclic ligand, there are some donor atoms. Minimum 3 donor atoms must be present. There are 4 most important biological macrocycles, which are porphin, chlorine, chorin and corphin. Porphin with some substitutions are called as porphyrins. Now out of all the 4 macrocycles that are present, the most commonly found one is the porphin. Since it is the most commonly found, we also call it as a workhorse macrocycle. What is the difference between what is the difference among all these macrocycles is, all the 4 macrocycles contain 4 pyrrole rings. We can see 4 pyrrole rings. Here also we can see 4 pyrrole rings. But the difference being, in these two, the 4 pyrrole rings are connected with 4 methane bridges. Here also we have 4 methane bridges. In the case of chorin, there are only 3 methane bridges. The 2 pyrrole rings are being connected directly without any methane bridge in chorin. Whereas in corphin, again the 4 pyrrole rings are connected with 4 methane bridges. And what is the another difference among these macrocycles is, in porphin there are 11 double bonds, and all these 11 double bonds are in conjugation. When it comes to the chlorine, there are only 10 double bonds that are in conjugation. In the case of chorin, there are only 6 double bonds, and these 6 double bonds are also in conjugation, but there are only 3 methane bridges with 6 double bonds in conjugation. When it comes to the corphin, there are only 5 double bonds, and these double bonds are not in conjugation. For our syllabus purpose, the most important one is the porphyrin, which is a derivative of the porphin. Well, for chlorine, we can have an example of chlorophyll, where magnesium is present in the active site in the center of this macrocycle. Vitamin B12, coenzyme B12 is an example for chorin, where cobalt is present in the active site. And coming to the corphin, there is nickel that is present in the core of this macrocycle. We call it as a MCMR, methyl coenzyme M reductase, which is not in our syllabus.